Welcome to clickmyproject.com. We are going to see the product for low power Split-Radix FFT processors using Radix-2 butterfly units. Next we are going to see the abstract for our product. An efficient combined single path delay commutator feedback Radix-2 pipeline fast Fourier transform architecture, which includes log 2 n-1 STD stages and 1 STF stage. The STC processing engine is proposed to achieve 100% hardware resource utilization by sharing the common arithmetic resource in the time multiplexer approach, including both adders and multipliers. Thus, the required number of complex multipliers is reduced to log 4 n-0.5 compared with log 2 n-1 for the other Radix-2 STC STF architectures. Fast Fourier transform has played a significant role in digital signal processing field, especially in the advanced computation systems such as orthogonal frequency division multiplexing and asymmetric digital subscriber. All these systems require that the FFT computation must be high throughput and low latency. Therefore, designing a high performance FFT circuit is an solution to the above mentioned problems. In particular, the pipeline FFT architectures have mainly been adapted to address the difficulties due to their attractive properties such as small chip area, high throughput and low power consumption. The two types of pipeline FFT architectures can be found in the split delay feedback and delay commutator. Further, according to the number of input data stream paths, they can be classified into multipath or single path architectures. The two classifications form four kinds of pipeline FFT architectures are often adopted when the throughput requirement is beyond the theoretical limitation, but the single path architecture can offer a given clock frequency over the concurrent read operations for the multipath input data. Therefore, single path architecture. The Radix-2 FFT architecture has a common observation that one half data do not involve complex multiplication at all, while the other half indeed involves complex multiplication. Hence, it has the opportunity to achieve the objective that reduces the arithmetic resource of a conventional complex multipliers by a factor of 2, leading to 100% utilization. It is ideal for two consecutive complex input data to contain a complex number which needs to execute complex multiplication. If so, we can minimize the reordering memory requirement by achieving the above objective that reduces 50% the arithmetic resource of complex multipliers. Next, we are going to see the flow diagram for our product. The given signal input database is given to the real and imaginary bit selection. Then the output of the real and imaginary bit selection is given to the input of the pre-stage transformation process. This process involves adder architecture, real and imaginary part, subtractor architecture, real and imaginary part, and the formula, the equation for the constant bits. Then the output of the pre-stage transformation process is given as input to the multiplier architecture results. The multiplier architecture results output is given to the input to the STC STF based node transform process operation. The output of the STC STF based node transform process operation is given as input to the post process transformation function. The multiplier requirement is approximate. The proposed design preserves the Radix-2 nature and achieves 100% multiplier utilization, while the other Radix-2 designs only achieve 50% utilization. Furthermore, the high Radix designs require more complex adders than the proposed design and can only process the FFT, whose size is the power of its high Radix. The 128-point FFT cannot be directly mapped to either one high Radix design, but the Radix-2 design can. Beyond the scope of this brief, the mixed Radix design can implement the 128-point FFT with relatively complex control logic. Since all of the FFT designs are single path, the throughput is 1 by n. Since the latency is roughly proportional to the size of the overall memory, the latency of the proposed design is 2n plus log base 2n-1. The critical path delay of the proposed design is Tm plus 2Ta plus 3T max, where Tm, Ta and Tmax are computation time of a multiplier, adder and multiplex. Finally, we are going to see the output for our product. To create the new file, we have to go to the file function and create the new file function. We have to specify the folder to which we have to save the file. The new source is created from the programming space. Then to simulate our program, click on simulation and main and double click on simulate behavioral model. The simulation process will be running. The FFT architecture is efficient and has low complexity levels. We see the output in the iSIM. There will be input data and the output data. To the input data, we have to specify the digital values. We have to specify the values. Here the force constant. We have to give the force constant's value. Then for the X2, the input is 8 bits. Then for the X3, the input is 8 bits. For the X4, the input is 8 bits. Similarly, the X5, X6, X7, X8, X9 is all 8 bits. The I specified in the folder all has the inputs data. We have to give the values. Then specify the constants values. Then run. The outputs will be created. Then minimize the options. Then for the implementation results, click on the implementation. And then again click on the implementation design and synthesis XSD. The synthesis report will be created. In that we can see the delay time of the program.